Swayam Prabha. Digital India. Educated India.
Okay, student, let's show you again this treatment effect on platinum electrodes that last class I taught first the gold electrodes. Now I will show you the pre-treatment effects on platinum, like platinum disc electrode, platinum nanoparticles. So how these all the pre-treatment effect or just after synthesis, how this aging effect can affect on electrocatalytic activity. That effect I will continue today. So again you can see the oxygen reduction reaction that I wanted to show you for the platinum electrode case, right? That you can remember the last class I taught you, like oxygen reduction reactions actually I will select for mainly platinum case, because platinum is very much active for oxygen reduction reactions, and for this reductions case we will choose 0.1 molar perchloric acid, because in this acidic media actually it is showing much better oxygen reduction reaction. I will show you now some effect on this oxygen reaction reactions. Let's see. First, as I told you, like you have the platinum disc electrode, and this disc electrode first we can use for mechanical polishing, cathodic treatment, anodic treatment, and then we will compare with sodium boride treatment. Okay, so let's skip first the sodium boride treatment. First, I wanted to show you if we compare like other treatment like mechanical polishing, like we have to polish the electrode on a pad and just make the aid and then clean it and just check the oxygen reduction reactions. You can see this one just after the mechanical polishing. Then we store this one for 1 day, 3 days, 7 days, or even the 1 month you can store it. Then you can check the oxygen reduction effect on the platinum electrode. You can see the cathodic treatment here. Cathodic means we will apply some negative potential or more negative scan. It means maybe you can take in the sulfuric acid medium, or maybe you can take the perchloric acid even. Then you can scan your platinum electrode in the negative window. For the 10 or 20 times you can scan, and that treatment can also activate your platinum electrode. You can see just after the treatment again you can see the high activity. So why I am saying this one high activity? You can see that it started the oxygen reduction, see in these potentials, and almost the highest reduction peak we are getting here, and see, but when we kept this electrode for longer time in laboratory environment, see the oxygen reduction start again towards the left. It means it is deactivated again after maybe 3 days, after 7 days. You can see it started actually from the left side. It means it is deactivated. And anodic treatment. Anodic treatment means again this is if it is the window of your potential scan. So this is the positive side, this is the negative side. So you have to go for some anodic treatment, means this positive side you have to scan for again 10 to 15 or 20 times you can scan, and then you can check immediately after the treatment. You can check oxygen reduction. You can see just after anodic treatment at the first glance it's showing something like this. Why? Maybe this is because of maybe because somewhat effect on the because of the oxidations, but just after one scan, if you go to the second scan, actually you can see the peak like this. So it is just the behavior on the platinum surface just after the anodic treatment, but still if you see like 1 day, 3 day, 7 day, there is very small change, very small change still you can observe. That also I will show you the surface phenomena, but just the result is this, that it may show you some deactivations. Now let's compare with the sodium boride treatment, because this is the very simplest treatment. For the platinum case, the oxygen reduction again is started in all cases. You can see the oxygen reduction started around here. So it means they are actually very much, but in the anodic case it's little bit positive side, it's reduction start. So then which one showing the best oxygen reduction reaction in this case, because it is started the reductions little bit right side, right? If reduction started right side means it is much better active compared to other three. But these three is almost you can say similar, but their deactivation is something different. See, for the sodium borohydride case and mechanical polishing case and cathodic case, but cathodic and sodium borohydride treatment in this case is almost the similar. But anyway, we can observe the activations, but they are not stable. This is the conclusion. Now let's see the factors that I am going to cover in here again. So mainly the platinum electrodes, not only this, here also I will cover some nanoparticles now. So why I am going to cover today again the lecture in the nanoparticles? Because as I mentioned, like just after the synthesis, if you coat this all the nanomaterials on the electrode surface, maybe immediately if you check the oxygen reductions, okay, if you check immediately oxygen reductions just after nanoparticle synthesis, you may see the reductions like this, but now these electrodes you just store it, then you may see the reduction again shifted. I am saying this is just the hypothesis. Now I will show you some result and then I will explain you for the nanoparticle case also, and then this activities why is depend on the aging, that also now I am going to explain for the nanoparticle case also. Okay, so just try to remember these activities actually not stable, that's why I am saying. So for the main today's talk keywords, let's go to the platinum all the electrodes. This is nanoparticles, nanoparticles, disc, okay, disc electrodes, also the maybe platinum coated electrode, platinum coated. So why I choose different substrate? Because when we will develop some lab on a chip, right, we will not use always the 100% pure platinum. There maybe we may use some glass surface, on that surface we will use some supporting material, on that surface then we will use some gold or platinum. Let's see their behavior. Maybe underneath that we are using some other material, they may also affect on the aging factor, they also can hamper their electrocatalytic activity. That's why we change, like from nanomaterial to disc to platinum coated, then we can see the actual phenomena and then we can apply this one on a lab on a chip design. So that's why when you will go for the keywords for this all the lectures, let's cover not like this way, like platinum nanoparticle, platinum disc, platinum coated electrode and their aging factors. Now let's come back. The oxygen reduction reaction for now disc and nanoparticles. See, as I told you, like although you are checking like disc and nanoparticle, let's compare in the different environment. You can store this disc and nanoparticle, you can compare one in the air conditions and another in the solution conditions. Solution condition means that I can say in the aqueous conditions. Why? You can dip the electrodes or coated electrodes inside a maybe aqueous solutions or inside a buffer solutions, you can store it. Why I am saying? Because platinum is highly active towards oxygen reduction reactions, but if you keep it the longer time in the laboratory environment, if somehow the platinum active side is blocked, very little contaminant, immediately you may see these deactivations. But if you store it in the solution stage, in the aqueous stage, these contaminations may come very slowly or almost no. Then you can easily decide this deactivation is because of the contaminations or not. And as I told you, we choose the oxygen reduction reactions because it's very rapid for the platinum case, and if there is any single and small change of the contamination, small deactivation, you can easily see this change. See, means just after see the sodium boride treatment, you can see it started here, but because of little maybe contaminations or maybe surface reconstruction, you can see it started from here. Little you can see this deactivation. But when these things means this activations we check in a solution stage, you can see this deactivation rate even after the 1 week is so slow, almost nothing. But if you go back, like last class I taught you this deactivation up to this much, it was started around here, this reduction in the ER case. So definitely platinum can show faster deactivations for the oxygen reduction reaction case if you store for the longer time in the year. This is a good information because as you know, another factor, the oxygen also the side reactions always in the biosensor, right? That's why I am teaching all this topic, where you have to understand all the side factors on your electrode surface, what's going on. That's why this few classes I am teaching this all the basic stuff. If you can understand like the electrode to electrode change, see, as I told you, the platinum electrode is highly active for oxygen reductions, right? So that's why you have to keep in mind, if you wanted to use the platinum, so you have to think about the oxygen reductions. Otherwise, you may get the higher background current. And you can remember the signal to background ratio is very important for your ultrasensitive biosensor. But if you want to use the platinum electrode, then you have to very much cautious about the oxygen reduction reactions. So let's tell you the probable reason again for the platinum case. Actually, this all the studies have done in the rotating disc electrode. Why we use the RD means rotating disc electrode, rotating disc electrode. So why is the rotating disc electrode? Then means generally what happened in a rotating disc electrode, in this mechanism your disc electrode will rotate in the defined RPM, means rotation per minute. So it will rotate and we will get the this current. Generally what happened, if you can remember, the reduction current generally is showing like this, but when you measure the in the rotation conditions, you will get almost the the linear in the case of the reduction, this linear current. So this is because a diffusions, this will be a very much constant, and you will get this phenomena only for the rotating disc electrode case, not for the simple case. In the simple case you may get like this reduction. So that actually we wanted to see the very sensitive change, that's why we use the rotating disc electrode. And the rotating disc electrode case, this is just a limiting current factor. I think this is just the equations why I use. That's why I wanted to show you that this oxygen reduction reaction that's happened on the platinum electrode and what the change happened on their active surface area. So these equations actually will show you that actually if there is active surface area is changing or not during the storage conditions in the laboratory environment. See, so this number of the electrodes, this A factors, this is the area factors, this all we can see from these equations, and from the experimental study you can compare the data. So here I wanted to show you, you can see, let's remove this, you can see the reduction zone. See, this is the reduction 0. Actually we start the 0.1 to 0.3 in this region, we scan. So from positive to negative, you can see the red one, that just before the sodium borohydride treatment, this region. So you can calculate the area in this region, and then just after the sodium borohydride treatment in this area. So this, if you calculate this reductions area, then we can measure that active surface area of the electrodes is blocked or not. So from these equations we can measure actually the active surface area of your catalyst or of your transducer surface. So, as you see from this curve that before treatment and after treatment, this surface almost similar, you can say, not that much change. Then what is the conclusion from here? That your active surface area is not changed. Active surface area almost similar, I can say almost similar before and after sodium borohydride treatment, right. Then why you are getting deactivations after the sodium borohydride treatment? That also we may have to think using our hypothesis, that is the surface reconstruction. That's why the surface reconstruction, this phenomena came for this aging effect. Although we may think the contaminations want the effect, and another thing why we are making this hypothesis surface reconstruction, because there is not that much change of the surface area. I will show you the XPS now. So, why to check the contamination, XPS can affect if there is a, mainly we may think any organic contaminations, right. See platinum region, so last class I showed you the gold region. Now I am showing you the platinum region, 72 in this region here, and here also another. Here you can see the platinum 2 peak, that's before and after, but here you can see the platinum peak is a little bit still change. From the electrochemical data also there is very small change, and from the XPS data is very small change still there after the aging. Carbon, we can say this is almost similar or small change. You can see after 7 days it's little bit, when after treatment you can see this one. If you see the nitrogen peak, oxygen peak you can see little bit increase, just after the before sodium borohydride treatment, then after the sodium borohydride treatment, and then after 7 days you can see little bit increase. It means there is some carbon oxygen material may be there, but it is not huge change. If it is there too much contaminations, maybe your peak, and this is just, I mean for the carbon case, carbon contaminations case, this is just after the treatment, and if it is, then you can see maybe the huge change of the carbon peak, but that is, it is not like this. So we can say it is not that much level. Now let us see the surface roughness change. Maybe after the storage for the long time, around 1 week or maybe 1 month, we may see some change on the surface roughness. You can see the RMS value again. This is the before treatment of this gold electrode surface, then after treatment, so 2.6 nanometer, 2.6 nanometer, again after 7 days almost 2.6 nanometer in the same surface. So it means you can from here you can conclude that surface roughness is not affected, right. It is not a factor for this electrocatalytic activity change. So that we can conclude from the AFM analysis. Now let us see for the disc electrode, for the coated electrode case, it is almost clear that they will deactivate and they will show you some contaminations issue. But let us see for the nanoparticle case, is there anything different for the nanoparticle case, or it is also similar, right. So from after this nanoparticle study, now we can say that this aging effect is really important for all the cases or not, but still we may need to investigate for some other material or other nanoparticle. But from here we can conclude on fundamental things, that we should not store your nanomaterial or your disc electrode, or maybe we can say in general your transducer surface for longer time. But if you want to store, which condition you have to store and how you are modifying the surface, that actually directly depend on your electrocatalytic activity may change during the time. Let us come to the nanoparticle. So here also again we checked oxygen reduction reaction in the acidic medium. So, here this is a transmission electron microscope image, or you can say the TEM. Here we synthesized the platinum nanoparticle after some chemical, like you can say the reductions method. Reduction method, as I think you can remember reduction method like ascorbic acid. So, you can use ascorbic acid, or you can try some other reducing agent like sodium borohydride also you can try. Then you may get some platinum nanoparticle. And from which salt you may get platinum nanoparticle? Here we are using chloroplatinic acid. Chloroplatinic acid. So, if you use this salt and then use this like ascorbic acid, sodium borohydride, then you may get something like this platinum nanoparticle. You can see they are very small size. So, the scale bar it is 10 nanometer. So, it means this size is really small, right? It is like almost 1 nanometer, something like this. Very small size nanoparticle you may get from chloroplatinic acid and after the reduction. And one thing I just tell you again, when you use this kind of reductions method for synthesis of platinum nanoparticle or any nanoparticle, you have to use some stabilizer. Otherwise, you may get some different result, or maybe deactivation may happen. Then you can claim that it is because of maybe agglomerations. What is that? If you not use here any stabilizer, generally we are using some sodium citrate as a stabilizer. What is the role of the sodium citrate? During the synthesis, when you add some ascorbic acid or sodium borohydride in the chloroplatinic acid, you can add sodium citrate. At the same time, when the nanoparticle will form and before the aggregation each other, this sodium citrate can help not to aggregate to each other. So, that's why we are saying sodium citrate is a stabilizer. They can stabilize. You can see this nanoparticle is not that much aggregate, but still you can see maybe one each other. This is because maybe if you use, when you take the TEM image, don't use very high concentrations. You have to use very low concentration. Otherwise, maybe one nanoparticle can overlap the another. That's why you can see dark color. This is because one each other they actually overlap. That's why you see this dark color. Otherwise, this nanoparticle almost they are almost separated because they are very good. They are stable nanoparticles. Why? Because during the synthesis, we are using stabilizer like sodium citrate. So, after the synthesis, let us drop this nanoparticle on a electrode surface. So, for example, here you can use indium tin oxide ITO coated glass surface. On that ITO coated glass surface, you can just drop cast your platinum nanoparticle here, and then you can dry it. But there is a one disadvantage. Just drop casting and washing the surface, so they can be detached from the surface. And you may think this deactivation may be because of the detachment of the nanoparticle from the surface, right? It's possible because platinum nanoparticle only give you the active surface area. If they detach, then definitely number of nanoparticle decreasing, active surface area also can decrease. So, you have to very much cautious. You have to think about the number of the particles should be the same, so that only you can compare. So, nanoparticle it is not like the disc electrode, not like the platinum pure electrode. So, in this case you have to think about that nanoparticles should not be detached from the surface, then only you can compare. So, one thing, that's why you can think like your ITO, indium tin oxide coated that glass surface you have, just after cleaning you can use some amine modification, amine modification NH2. How you can do the amine modification? So, that I already taught you in the very first class. You can see that we can modify some amine molecules, then and also you can use some dendrimer. They also have some amine dendrimer or some amine related things you can try. Now, This amine and nanoparticle, this gold or platinum, they have some interactions. So, they will be very easily, they will be attached on the surface and they will not easily detach when you will wash, because you need some washing, no? So, when you are washing the surface just after synthesis, they will not easily detach. That is why it is recommended when you drop some nanoparticle, let us use some linker, this kind of linker you can use. They will help bind the nanoparticle on the surface. Now, let us check just after synthesis, you see when we check the oxygen reduction, here we are not using the rotating disc electrode, because your chief that is ITO chief that is coated the platinum nanoparticle, it is very difficult to rotate them. That is why last time we saw the oxygen reduction reaction something like this. This is kind of limiting current. This is kind of limiting current, but here we are getting like simple reductions, like the cyclic voltammetry as I taught you know last class. Like we will get, like here also we check the cyclic voltammetry only, because we started from right side and then we scan towards the left. So, stopped here, then again oxidation, but here we are not getting any peak oxidation peak, because we just tried the oxygen reduction peak. There is no other substrate so that they can show the oxidation peak. Slowly you are understanding, right? So, sometimes that is why we are measuring only this scan, reduction scan. No need to measure the oxidation scan, because your oxidation peak or not peak, no peak here, your oxidation scan is not that much informative. It is not giving any kind of information. So, you can eliminate the oxidation, that is why scan, just reduction scan you can make. This is called the, as you are taking here reductions and then oxidations, that is why it is cyclic voltammetry. But when you are taking only reduction, this is just a one scan, this is called linear sweep voltammetry. That is cyclic, this is a linear sweep, only one sweep. So, here also as usual, like chemically synthesized case, just after synthesis you can see the very good reductions of the oxygen, and then after 1 day, then after 3 days and 7 days, there is some change again we can see in the case of nanomaterial. It means your nanomaterial coated surface, but here actually also we kept in the air. So, if you keep this surface in the air, this surface also not that much stable. So, if you, that is why if you modify some sensor surface, you have to think about, if you like, if your surface is very much highly dependent on the oxygen reduction reaction, then you have to be careful. That is why you should not try with your platinum electrodes in this negative region. So, it is recommended, let us go to the right side, so that you may not see the oxygen effect. That is why I am just teaching this all the phenomena. So, here again in this, this is the SEM image, I am just showing you in this case. This is the another image. Why I am showing this one SEM image? Because in this case we deposited the platinum nanoparticle on the electrode and ITO surface electrochemical. It is the electrochemically deposited one. Electrochemically deposited. Okay, and this one chemically synthesized. So, electrodeposited one case means as it is already on the surface. So, we cannot take the TM image, let us take the SEM image, because it is a solid surface you can take, and in this case we are taking just, it is the solution we are dropping on a TM grid, and there we are taking TM image. But in this case, SEM case, you may have a big surface, maybe 1 micrometer by 1 micrometer. In this region we can take the image, and in this case we can see still here the platinum nanoparticle size something different for the electrodeposition case. There, as I told you, last time, that we can tune the activity by based on the size, based on the shape, based on their morphology, like alloy type or core cell type. But is this kind of nanomaterial still showing the aging effect or not? That is why we check the electrochemically deposited one also, and here also we can see that this one also again is deactivated after some longer time. So that's why it is not recommended this kind of electrode surface to keep for the longer time in the room temperature. Okay, now that's all for the platinum case. Now I will come back again the other electrodes like printed circuit boards and use them for the again modifications for biosensor development, and let's see is this kind of side effect really affecting on their background current or not. Mainly why I am teaching this one, this all the deactivation treatment is the factor is the reliability. Reliability means your reproducibility. Reproducibility means if you want to commercialize your sensor surface, so if you develop today, is tomorrow you will get the similar result or not. So if not, it is not reproducible, it is not reliable, nobody will accept this development, you cannot commercialize. That's why I taught you all the phenomena. Okay, that's all for today's class for factor effect on the pretreatment or some other case for gold, platinum, disc and nanoparticle. Next class onward, then again I will come to development of the sensor surface based on these factors, so that we can avoid and we can develop some very good, reliable and reproducible sensor. I think you understand the factors that are affecting on the reproducibility. That's all for today. Thank you.